All right, so we'll continue. I just noticed that in notes, I use S and X. So maybe I change it back to the notation in the notes. Otherwise, somehow you may get confused. Okay, so let's just change A to S. So that's one the X. So then it will be same as in the notes. So that's S. All right, so that's the idea of reflexiveness. It's related to itself. Every element is related to itself. The second important property is called symmetry. So it's symmetric, dealing with symmetry. It's M. So I suddenly expect it's not quite sure about the M. Okay, symmetry. So it's dealing with symmetry. It's symmetric means for every pair X, Y, if X is related to Y, then Y is also related to X. Or maybe I write it this way. That one direction will be okay. Whenever X related to Y, Y is related to X. So for every such pair. So that means if we have arrow from X to Y, we must also have this one. We must have this one. All right. So for every pair, we must have this one. So it's both directions. So in other words, we don't have the following structure. So this arrow there, but without this arrow, without this one. So also noted. So without symmetric means we don't have such structure. So every the arrow must be both directions. Okay, so in terms of these relations, this one is symmetric, but none of these two are symmetric. Only this one is symmetric. Equality, this one is symmetric. So this one is not symmetric. This one is not symmetric. All right, I'll give you more examples. Okay. Another one related to symmetric is anti-symmetric. It's not asymmetric, but rather anti-symmetric. Anti-symmetric. All right. So that means if X related to Y, then Y should not be related to X. If X related to Y, then Y is not related to X. We did not give a notion of not related. Maybe just writing this way. Okay, not Y. In other words, if both X related to Y and Y related to X, then the conclusion is these two must be same. So these are equivalent. The anti-symmetric means for any two, if we have this one, then we cannot have the other one. Anti-symmetric means we cannot have the other one. So between every pair, either they're arrow from X to Y or from Y to X, or there are no arrows. The situation will be look like this. So for any pair, we cannot have both. So we cannot have this one and this one. So that is not allowed. Now this one for anti-symmetric. Okay. So for every pair, it must have this one. So these three, 1, 2, 3, these properties are quite simple, very basic properties. And next one is very important. It's called the transitivity. Some I use adjectives. Oh yes, and I should say transitive, not transitivity. Uh, Dealing with transitivity. What it means, now we deal with three elements, x, y, and z inside X. What happens is if x related to y and y related to z, then we must have a case that x related to z. That's called the transitivity. Actually, that's one is easy to explain. And many relations have this property. It's even more easier than this one to explain it. The transitivity means that if we have x here, y here, and z here, so that means if I can get from A to Y and from Y to Z, that means I must be able to get from ZX to Z. So that's transitivity. The transitive means as far as I can get from X to Y and Y to Z, and I can get from X to Z. So this one must be out in the relation. That's called the transitivity. All right. Many relations are transitive. For example, less than or equal, less than, subset sum, subset sum. These relations or the divisibility, all of them transitive. So 2 divides 8, 8 divides 64, that implies 2 divides 64. This transitivity. All right. 3 is less than 5, 5 less than 10, so that implies 3 less than 10. So that's transitivity. All right. Okay. So these are four fundamental properties, and it's very important and fundamental, and the combination of them give us something very, very useful. So, for example, equivalence relation and partial ordering are really based on these fundamental properties, which we will discuss. We will discuss in a minute. Okay. No, sorry, partial order not in a minute. On Wednesday. All right. Now I will give you quite a few examples to see if you fully understand these four properties, because really they're very important. We have to understand them first before we go further. Okay. Okay, we have these four properties: reflexiveness, symmetricness, and antisymmetricness, and transitivity. All right. So let's see. I give you some relations. Let's see if you can figure out whether they have these properties. I give you quite a few, 7. Right? In the notes, I give 7. So we consider some relations, some equality relation for these four elements. The graphic representation look like this. Okay, I give you some time to think about what property does this one have. Among these four properties, which properties this relation has? Set size. Okay. If we can figure out all of them, then that means you understand the definition of these four fundamental properties. Okay. Oh, it's already there. Okay, maybe we'll go over these three first. I see a question. Yeah, that's a very good question. One should ask whether relation must be symmetric or anti-symmetric, and no. There can be something in the middle. Because symmetric and if symmetric, require every pair has that property. So some pair may not satisfy both properties. There is something in the middle, okay? So you can either draw an example. Okay. All right, so for these three, so it's very simple. Let's see which properties they satisfy. So this one, of course, is reflexive because each one has a small loop with it. That's one. So in this case, it's both symmetric and anti-symmetric, both 2 and 3. And it's also transitive. Actually, it's trivially transitive. Because for all triples, the triple must be itself. So x, 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 y, y, y. So 1, 1, 1, 2, 2, 2, 3, 3. So you see this loop. And we cannot use different number, otherwise there are no such edge, because there are no such edge. So for this one, it's 1. It's not symmetric because there are edge from 1 to 2, but no arrow from 2 to 1. So it's not symmetric. It's anti-symmetric because for each one, we have only one. For each pair, there's only one arrow. At most, one arrow. So that's anti-symmetric. So tentative takes some time to decide. So for example, this one from 1 to 2 and 2 to 3, so we have 1 to 3. Okay, the other combination 2 to 3, 3 to 6, we have this one. So if you look at the picture, it takes some time. But from this relation itself, definition itself, it's quite clear. X less than y, less than or equal to y less than or equal to z means x less than or equal to d. So it's this one. So this one is almost same as this one, except it's not reflexive. We don't have loops. So it's 3 and 4. Okay, so see, it's not difficult at all. Just be careful. The most difficult thing to decide is whether it's transitive. Sometimes it's not obvious. All right, give you a few more examples. I don't think I want to go over all of them. The middle two, I will leave it for yourself in the notes. Just to give you two more. So here, x and y are x related to y if their sum is a prime number. So these four numbers, okay. So this is a graph for the relation. All right. So 2 plus 3 is 5. It's a prime number. 1 plus 6 is 7. It's a prime number. 1 plus 1 is 2. It's a prime number. 1 plus 2 equals 3. It's a prime number. 3 plus 6 is not a prime number. It's 9. So we don't have any error at all. 2 and 6 is 8. So it's not a prime number. So that's the graph we get. All right. Now this one is not reflexive. It only has loop for 1, not for 2, 3, and 6. But it's symmetric. You see, whenever there edge between different ones, there another edge in the opposite direction. So we have an arrow in this direction, we have an arrow in the different direction. So 2 is satisfied, it's symmetric. It's not anti-symmetric because we don't have edge in one direction only. So without this one, we don't have that situation for every edge. So certainly it's not anti-symmetric. Yeah. Now, where is the transitive? So here is a counter example. 3 related to 2, 2 related to 1, but the 3 is not related to 1. So it's not transitive. If it were transitive, we will have this edge. But we don't have this edge. So or arrow, so it's not transitive. It's not transitive. So this one is symmetric, but not none of the other three. Okay. And then finally, one more example is okay. So that's a graph we obtained for this relation, the graphic representation. So for example, one is related to itself because if we replace x and y by one, so one is at least one. So one is related to itself. Now three related to two because here two times here is three. This side is three more than three, but two is not related to three. Here two, here three. Okay, hold on. Did I just be two x y two related to? Oh yeah, two is not related to three. If x is two, y is three. So here this side will be five. So we don't have this arrow. Okay, so that's graphic representation. Okay, so this one is easier to see, not reflexive, because we only have loop for one. It's also not symmetric, because symmetric for this one we need to have this edge. So it's not symmetric. It's anti-symmetric because for each edge we see, so each arrow is goes in one direction. We don't have arrow in another direction. So sorry, I keep on talking about edge. Okay, it's the reason is later on when we describe these things will be called edges or arrow. That's a term we use for graphs. Edge or arrow. All right. So it's anti-symmetric. Now, for transitivity, in this case, it is, but it takes time to check. For example, this one goes to 3 and 2, so we have this one. For this one, goes from 3 to 2 to 1, we have this arrow. So we have 6 goes to 2, then to 1, we have 6 to 1. So that's quite a small, only 4. Even we try all possibilities, you can check. Indeed, it satisfies the transitivity. All right. So eventually we know this relation has these two properties. All right. Okay. So these are all very important basic properties, and they're very useful and important. As we will see in the next very important property called equivalence relation. All right. The relation is equivalence relation if it satisfies the following three properties. It's reflexive, symmetric, and transitive. Such a relation is called equivalence relation. So the reason is these elements, in a sense, they're equivalent. That's why it's called equivalence relation. So common example is this relation. Now you see where equivalence come from. Equality. That's the equivalence relation. On real numbers or on integers, on qualitative integers, on rational number, all of them are define equivalence relation. All right. So let's say on integers. we define relation on integers so that x related to y if only if the sum is even number. Just define the equivalence relation because certainly it's reflexive. X plus x equal to x, or even. It's certainly symmetric because x plus y equal y plus x. All right. Now we can check the transitivity. So if x plus y is even, y plus z is even. All right. So we can see that the summation x plus y plus z is also even. So transitivity means this. I found it. X, not, not sum of these three. X plus z is even. Not summation of these three. Okay. Sorry. All right. So if x related, y related, yc related, then xc is related. So if that's the case, then it's tentative. Of course, it's easy to see it. So if these two are even, either both of them are even or both of them are odd. They have same parity. So x, y, so that means x, y have same parity, same parity. Either both even or odd. So here that's what means y, z, same parity. Okay, now the key point of transitivity is this facial thing common element here. So it's transitive. It's transitive through this element. So x, y has same parity. So in a sense, x, y same, y, z same. Of course, we can say x and z are same. So x, z same. X, this one is even. So therefore, this relation has all three properties. So it's defined equivalence relation. All right. Another example is important one. It's a concurrence relation modular n. So that's why actually special name for it, Rn. Usually people use Rn. All right. So for example, n equals 3. So that what does that mean? That means reminder when we divide the number by 3, then these two numbers will have same reminder. So for example, say 3, 6. They're related because the reminder divided by 3 is same, 0. So 4 will be same as 7. The remainder will be 1 when divided by 3. So 2 will be same as 8. Okay. So this relation is also reflexive. That's obvious, also symmetric. Because when AB is a multiple of n, B minus A. So A minus B is a multiple. So if this one means this one. Okay. So that's same as A divided B minus A. So that's why it's symmetric. All right. Now it's transitivity. So we can use algebra to see it. So if n A minus B and C. All right, then that implies n is divisible by A minus C. Okay. So it's easier to see it because if the remainder when A and B divided by N is same, and the remainder of B and C are same divided by 3. Of course, the remainder of A and C will be same. So it's easy to see it by if we look at the remainder when the number divided by N. Okay. So this relation is also reflexive, symmetric, and intelligent. Therefore, it's also equivalence relation. All right. So why equivalence relation? What's the meaning of this one? So we define it in this way. In terms of these three relations. So given a particular relation, we can check to determine whether it satisfies these three properties. If they satisfy, then it gives us the equivalence relation. But then so what? What's the usefulness of equivalence relation? Why do we need such a relation? So that's the important question behind it. Why do we define such a relation? Really, because it's very important. Then we can see if we look at these things. This one is quite trivial. Okay, this one is too trivial in terms of the next concept of partition. If we look at these two relations, there are one important property of these two relations. Look at this one. This one, actually, if we consider all integers, this one divides or partition integer into two parts, namely odd number and even numbers. If we look at this one, okay. If we look at this one, actually the partition the integers into two parts, one odd numbers, one even numbers. For all number inside one set, any two, if we take out any two of them, they will belong to this relation. So here odd number. For any two odd number, their summation will be even. For all two even numbers, their summation will be even. But if we take one number from this part, one number from this part, their summation will be an odd number. So they're not satisfied relation. So for any two, any two numbers either both belong to this part or both belong to this part. All right. So they have this property. They are unable to partition all the elements into two parts with this property. And similarly, look at this one. This one allows us to partition. Let's see. In the notes it's 4. Okay. So I will use 3. Okay. So here is partition all numbers similar to this one. To even order, here is partition integers into 3 parts. Depends on the remainder. So all numbers divisible by 3. All right. Then the remainder, when divided by 3 is 1. And then all divided by 3 is 2. Again, it has this property. All pairs, if they're related, they either belong to this one, or this one, or this one. What happens is we can divide things to several parts, and the elements in this part have similar property, the same property, similar property. So here, everything here is odd, everything here is even. Here, every element here is divisible by 3. Every element here, and any integer here, the remainder when divided by 3 is 2. Here is 1. So they share common properties. All right. So this class, this sort of relation enable us to divide set into disjoint sets, and each set has similar property or same property. So that's the importance of equivalent relation. Okay. So let me make it more mathematical. What we mean by these things. All right. So, For this one, actually, in particular, it's every number is itself. Okay. So we have an equivalence relation R. All right. So once we have a relation, actually any relation, we can construct a subset of elements with this definition. The function R. So any elements that's related to Y will be put into inside this one. So for equivalent relations, this set is called equivalent class. So this equivalent class determined by this X. Right? So for example, here, so this equivalent class defined by say 1. Actually, any member here can be used as that X. So say, typically we pick a simple one, here maybe 1. So after 3, minus 3 is still same, also same. Equivalent class defined by this one is also this one. So similar for this one, normally we use 0. Anything else is okay. So for example, 2. So these are equivalent classes. All right. So this module relation is defined congruence space, same as similar to this one. For example, this one. So each member can be regarded as a representative of this whole set, subset. So here we can use maybe 3 to denote remainder divided by 3 is 0. So either 3 or 0. So this gives us equivalence classes. So here maybe 1, here 2, and so on. Okay. So from equivalence relation, we have such equivalence classes. So what is important about this relation is equivalence relation partition the set into equivalence classes. So that's the important thing. Yeah. So the important thing is the notion of partition a set. That's equivalent to partition of a set. So how do we partition a set? When we say partition of a set, so it's this X, we partition it into disjoint sets. So we partition all elements into disjoint sets. So that's called a partition. Suppose it's here 1, 2, maybe 3, so here 4. So that's a partition of a set. A partition of a set. So it's a collection of a subset of S. Partition of a set is a collection of disjoint sets of S. So they all together equal exactly S. So they are whose union is exactly S. So partition them into different subsets, such that for any two subsets, the intersection is zero. So they do not share element. Okay. And all subsets together, they form the union. Their union is exact equal set. That's called a partition. All right. So a partition of a set. So mathematically, it's just with a partition. So if S1, S2, maybe SK, mathematically, just one partition of S. So what it means is their intersection is empty for any I not equal J. So that's one thing. Second thing is the union of all of them equal exactly S. So that's the meaning of partition. Of course, all these sets are non-empty sets. So partition, so somehow that's uniquely defined. Otherwise, if I allow empty sets, that's useless, right? So none of the sets is empty. So that's called a partition of a set of S. So equivalence relation has a very, very close connection with partition. Actually, same thing. Equivalence classes is the same idea of partition, but in two different ways. So let me make it clear mathematically. If there are two theorems, I want to mention it. Yeah, use one of. Okay. Let me check my. Let's see. Yeah, in my notes it says theorem 2.3. Maybe I follow the name in the notes. Otherwise, you may get confused. So the notes it says 2.3. Okay. So we have equivalence relation on the set S. Then what we have is okay. So what does that theorem mean? Actually, if you recall the previous example, so we have equivalence relation on X. Then for any two elements, then two elements are related if only if the equivalence class defined by these two elements are same. They call the even order example. So we have all the number, even number. So -3, -1, 3. So that's the even number, odd number example. All right. So that one means two numbers related if only if they're in the same class. So they're class of same class. So as I mentioned earlier for this one saying this equivalent class can be developed by any member inside. For example, all of these will be same as this one. So this one will be same as equivalent class defined by say 0 or 2 or -4 and so on. So that's the meaning of this class. Two elements related if only if they're in the same class. All right. Now that it follows actually that two equivalent classes are either same or they're disjoint. These are disjoint. They cannot share elements. All right. I don't think I have time to go over the proof. The proof itself actually is very, very simple. But to write it formally, it's kind of tedious. It's quite short. I think I would rather leave it to you to take a look if you're really interested in the proof. The proof actually very simple. Basically, based on this idea, transitivity. If these two classes share one element, if they have one element in common, that there are x here and x here, then these two classes will be merged into one because of transitivity. So really, the transitivity. These two are simple things. Mainly by transitivity. If these two classes share one element, then because they share one element, these two classes will become one. So they must be disjoint. They cannot share any element. So that's the meaning of this one. So any two classes, they cannot share. So they must be same or say disjoint. Right? Okay. So that's an important property of equivalence relation. This property actually defined a partition. I think I will delay to Wednesday because maybe a little bit subtle instead of rushing it through. It takes another 5 minutes or so. I think I will leave it to Wednesday. The notion of equivalence relation and the partition of a set actually means the same thing. If you think by yourself, actually you can feel it from these two things. You can feel it already. It's a partition. Because of this property, mainly because of this property, it's a partition. Because two elements are related, they will define same class. So basically, they will define the partition of elements. So therefore, eventually, the notion of partition and equivalence class actually the same thing. All right. So I will delay to Wednesday to give a little bit more discussion on that to tell you where that they're really same thing. And later on, we'll use this notion to define some term like connected components when we discuss graph theory. Another way to define connected components in a graph actually is use equivalence relation. All right. I think I will stop here. So we'll spend a few, maybe 5 up to 10 minutes on Wednesday on equivalence relation again, its relation with partition, and then discuss the partial orderings on Wednesday. Okay. All right. I think I will stop here. Thank you. See you on Wednesday. Oh, by the way, in the homework, it's a homework 4 already, right? So one question about it's x plus y plus c. It's a 9 or 10 or something. That's the same thing. Even 100 does not matter. Okay. I really encourage you to do this question by yourself. Don't ask anyone. Don't read the textbook. Of course, you forget our discussion of combination and the computation with repetition. You may want to take some time to give a review to understand what the combination of computation by repetition. Then try to find the answer for this one by yourself. So there are two questions about this one: a number of different terms and the coefficient about a particular term. And it's very, very useful to find a solution to this question by yourself. Once you find out how to do it, you understand the repetition and commutation sorry, a combination and commutation with repetitions. I really encourage you, strongly encourage you to think about this one. Actually, it's not difficult. It's simple. Once you understand what's going on, it's quite simple. But it's not easy, very easy to really fully understand what's going on, to see it, to see the connection between these two problems with the ball box model. So I really strongly encourage you to do it by yourself. Think about it by yourself. Okay? Try to find a solution by yourself. Right? Okay? So see you very later.